Welcome to GKE SNAT and IP Masquerade. Welcome to the channel. Please consider subscribing. I produce videos covering AWS, Azure, and GCP on a daily basis. Please also hit the bell button to get notified. Welcome everyone. Today we're diving deep into one of the most critical yet often misunderstood networking concepts in Google Kubernetes Engine, SNAT and IP Masquerade. This isn't just theoretical knowledge. Understanding this will save you hours of debugging production network issues. Think of this as learning about your cluster's corporate ID badge system. Just like employees need different forms of identification for different situations, an internal badge for the office, a business card for external meetings, a driver's license for travel, your pods need different IP addresses depending on where they're communicating. By the end of this presentation, you'll understand exactly when and why GKE changes your pod's IP address, how to troubleshoot masquerading issues, and most importantly, how to configure this behavior to meet your specific networking requirements. We'll cover both the traditional config map approach and the newer egress NAT policy method. The core problem. Let's start with the fundamental networking challenge that every Kubernetes cluster faces. When you create pods in GKE, they get assigned private IP addresses from your cluster's pod CIDR range. These might look like 10.48.1.5, 10.48.1.6, and so on. These addresses work absolutely perfectly for communication within your cluster. Pod to pod, pod to service, everything internal works beautifully. But here's the problem. These private IP addresses are completely meaningless to the outside world. It's exactly like having an internal employee ID number like employee. That number is perfect for your company's internal systems, but if you try to use it as identification at another company, it means absolutely nothing. This is where IP masquerading comes in. It's GKE's sophisticated way of giving your pods a recognizable identity when they need to communicate with external systems. The technical term for this is SNAT, Source Network Address Translation, which literally means changing the from address on network packets. Understanding the corporate analogy. I love using analogies to explain complex technical concepts, so let me paint you a detailed picture. Imagine you work in a large corporate office building. Every employee has a specific desk location like Building A, Floor 4, Wing B, Cubicle 3. That's incredibly specific and useful for internal operations like mail delivery, finding colleagues, or booking meeting rooms. But when you need to attend a meeting at another company across town, you don't show up and say, "Hi, I'm from Building A, Floor 4, Wing B, Cubicle 3. Instead, you present your business card with your company's official address. Something like 123 Corporate Plaza, Suite 500. An address that's meaningful and recognizable to the outside world. That's exactly what IP masquerading does for your pods. The pod's internal IP address is like your cubicle location. Perfect for internal use. But when that pod needs to make an API call to an external service, download a container image, or connect to a database outside the cluster, GKE's networking layer swaps out that internal cubicle address with the node's official corporate address. An IP that external systems can route to and understand. GKE's default masquerading rules. Now, GKE isn't random or arbitrary about when it performs this masquerading. It follows a very specific, intelligent set of rules that Google has carefully designed based on common networking patterns. Let me break down exactly how these rules work in practice. Rule number 1. When pods communicate with each other within the same cluster, GKE does absolutely no masquerading. This is like employees walking between cubicles in the same office. They can use their internal desk numbers directly because everyone understands the internal addressing system. Pod 10.48.1.5 can talk directly to Pod 10.48.1.6 using those exact addresses. Rule number 2. When a pod sends traffic to the public internet, maybe calling the GitHub API, downloading from Docker Hub, or making HTTP requests to external services, GKE always masquerades the traffic. Every single packet gets its source IP changed from the POD's private address to the node's public or VPC routable address. Rule number 3. And this is where it gets tricky. For private network destinations like other virtual machines in your Google Cloud VPC, on-premises networks connected via VPN, or resources reachable through Cloud Interconnect, GKE's default behavior is to not masquerade. This preserves the original pod IP, which can be exactly what you want, or exactly what causes problems, depending on your network security requirements. Deep dive into the masquerading process. Let me walk you through exactly what happens at the packet level during masquerading, because understanding this process is crucial for troubleshooting network issues. When your pod, let's say it has IP address 10.48.1.5, decides to make an HTTP request to google.com, here's the step-by-step process. First, your application creates a packet with source IP 10.48.1.5 and destination IP 172.217.164.142, one of Google's IP addresses. This packet travels through the POD's virtual Ethernet interface, through the node's networking stack, and reaches what's called the IP masquerade agent. The IP masquerade agent is a critical component running on every GKE node. It examines every outgoing packet and asks, does this destination match my masquerading rules? For traffic to 172.217.164.142, public internet, the answer is yes. Here's where the magic happens. The agent modifies the packet header, changing the source IP from 10.48.1.5 to the node's IP address, let's say 10.128.0.10. It also creates a connection tracking entry so that when Google's servers respond, the traffic can be properly routed back to the original pod. This entire process is completely transparent to your application. Your pod thinks it's communicating directly with google.com using its own IP address, but from Google's perspective, the traffic appears to come from 10.128.0.10. When the response comes back, the masquerade agent reverses the process, changing the destination from 10.128.0.10 back to 10.48.1.5 before delivering it to your pod. Real-world problem. Enterprise network security. Now let me describe a real-world scenario that I've encountered multiple times in enterprise environments, which perfectly illustrates why understanding IP masquerading is so critical for production systems. Imagine you're working for a financial services company that has strict compliance requirements. Your GKE cluster needs to connect to an on-premises database that contains sensitive customer billing information. Your security team has implemented very granular firewall rules stating that only the billing application pods are allowed to access the customer database. Logging pods, monitoring pods, and any other applications should be blocked. This seems reasonable. You want to minimize the attack surface and ensure that only authorized applications can access sensitive data. Your security team has even identified the specific IPs that should be allowed. The billing pods have been assigned IPs in the range 10.48.1.0/28, and the firewall rules specifically allow only this range. But here's where the problem emerges. Your billing pod with the IP 10.48.1.5 and your logging pod with the IP 10.48.1.6 both happen to be scheduled on the same Kubernetes node, which has the IP address 10.128.0.10. When both pods try to connect to the on-premises database, if masquerading is enabled for private network traffic, both connections will appear to come from the same source, the node's IP address 10.128.0.10. The on-premises firewall now faces an impossible decision. It sees two connections, both apparently from 10.128.0.10, but it has no way to determine which one is from the authorized billing application and which is from the unauthorized logging application. It can either allow both connections, violating security policy, or deny both connections, breaking the billing application. Detailed problem analysis. Let me break down this problem scenario with precise technical details, because understanding the exact packet flow is essential for designing the right solution. Here's what happens step by step. Your billing pod at 10.48.1.5 creates a database connection to 192.168.100.50, the on-premises database server. The packet leaves the pod with source IP 10.48.1.5 and destination IP 192.168.100.50. This packet travels to the node's IP masquerade agent. Now, if you've configured GKE to masquerade traffic to private networks, which many organizations do for various networking reasons, the masquerade agent says, "This is an outbound connection, so I need to masquerade it." It changes the source IP from 10.48.1.5 to the node's IP 10.128.0.10. Simultaneously, your logging pod at 10.48.1.6 also tries to connect to the same database. Maybe it's trying to log database access attempts or performance metrics. Its packet also gets masqueraded from 10.48.1.6 to 10.128.0.10. The on-premises firewall receives two connection requests, both with source IP 10.128.0.10 and destination IP 192.168.100.50. From the firewall's perspective, these are identical connections. There's no way for it to distinguish between the authorized billing traffic and the unauthorized logging traffic. This forces a binary decision. Either create a firewall rule that allows 10.128.0.10 access to the database, which allows both applications, or deny access from 10.128.0.10, which blocks both applications. Neither option achieves the desired security posture of allowing only the billing application. Solution strategy. Selective masquerading. The solution to this problem is both elegant and powerful. We need to tell GKE's IP masquerade agent to be selective about when it performs masquerading. Specifically, we want to say, for traffic going to the public internet, please masquerade as usual. But for traffic going to our trusted private networks where we have granular firewall rules, please preserve the original pod IP addresses. This gives us the best of both worlds. Internet-bound traffic continues to be masqueraded, which is important for security. We don't want to expose internal pod IPs to the public internet. This is also important for functionality, as many internet services expect traffic to come from routable IP addresses. But for our carefully controlled private networks, we preserve the pod IP so that firewalls can apply granular, application-specific rules. GKE provides two mechanisms to achieve this. The traditional config map approach, which has been available for years and provides global cluster-wide configuration, and the newer egress NAT policy approach, which gives you fine-grained, application-specific control. Let's start with the config map approach since it's simpler to understand and widely used. The config map approach works by creating a special configuration object in the kube system namespace that the IP masquerade agent automatically monitors. When you create or update this config map, every masquerade agent on every node picks up the new configuration within about 60 seconds and starts applying the new rules to all outbound traffic. Config map deep dive. Every line explained. Now, let me walk you through the config map configuration line by line, because understanding every element is crucial for getting this right in production environments. We start with the standard Kubernetes resource definition. API version v1, kind config map. This tells Kubernetes we're creating a configuration data object. The metadata section is critically important. The name must be IP mask agent exactly. This isn't arbitrary. The IP masquerade agent specifically looks for a config map with this exact name. The namespace must be kube system. This is where GKE stores system-level configuration, and it's the only namespace where the masquerade agent will look for its configuration. If you create this config map in any other namespace, it will be completely ignored. The data section contains a single key called config with a YAML string value. This config string defines the actual masquerading behavior. Let's break down each parameter. Non-masquerade CIDRs is the heart of this configuration. It's a list of IP address ranges, in CIDR notation, that should not be masqueraded. When the masquerade agent sees outbound traffic to any destination in these ranges, it preserves the original pod source IP. The first entry, 10.48.0.0/14, represents your cluster's pod IP range. Including this ensures that pod-to-pod communication within the cluster never gets masqueraded, which is the default behavior you want to maintain. The second entry, 10.128.0.0/9, typically represents your Google Cloud VPC's primary IP range. This ensures that traffic from pods to other virtual machines in your VPC preserves the pod IPs, enabling virtual machine-level firewall rules to distinguish between different pods. The third entry, RFC 1918, represents the on-premises network range in our example. This is the key addition that solves our firewall problem. Traffic to the on-premises database will now preserve pod IPs. Masquerade link local is set to false, which means link local addresses 169.254.0.0/16 won't be masqueraded. This is generally what you want for proper cluster networking. Resync interval is set to 60 seconds, which means the masquerade agent checks for configuration changes every minute. This determines how quickly configuration updates take effect across your cluster. Applying and verifying the configuration. Now let's walk through the complete process of applying this configuration and verifying that it's working correctly. I'll show you every command you need and what to expect from each one. First, save the YAML configuration to a file. I always recommend using a descriptive file name like ipmaskagentconfig.yaml so it's clear what this file does when you encounter it months later in your infrastructure repository. The kubectl apply command creates or updates the config map in your cluster. When you run kubectl apply -fipmaskagentconfig.yaml, kubectl will show you config map/ipmaskagent created if this is the first time, or config map/ipmaskagent configured if you're updating an existing configuration. To verify the config map was created correctly, run kubectl get config map ipmaskagent -in kubesystem. This should show you the config map with an AGE indicating when it was created. You can also run kubectl describe config map ipmaskagent -in kubesystem to see the full configuration details. But here's the critical part. You need to verify that the masquerade agents actually picked up the new configuration. Run kubectl get pods -in kubesystem -lkatesapp equals ipmaskagent to see all the masquerade agent pods. There should be one pod per node in your cluster. Then check the logs. Kubectl logs -in kubesystem -lkatesapp equals ipmaskagent. Look for log messages like loaded configuration or updated rules that indicate the agent successfully loaded your new configuration. If you see error messages, they'll typically tell you exactly what's wrong with your CIDR ranges or YAML syntax. To test that the configuration is actually working, you can create a test pod and use commands like iproute or TCP dump to verify that traffic to your specified ranges preserves the pod IP while traffic to other destinations gets masqueraded. This is especially important in production environments where you need to be absolutely certain the configuration is working as expected. Observing the solution in action. Now let's examine exactly what happens once our configuration is in place and working correctly. This is where you can see the power of selective masquerading in solving real-world networking problems. When your billing pod at 10.48.1.5 now attempts to connect to the on-premises database at 192.168.100.50, The masquerade agent examines the destination IP. It checks its non-masquerade CIDRs list and finds that 192.168.100.50 falls within the 192.168.0.0/16 range that we specified. The agent makes the decision. This destination is in my non-masquerade list, so it'll preserve the original source IP. The packet travels to the on-premises network with source IP 10.48.1.5 intact. When it arrives at the firewall sees a connection request from 10.48.1.5 to 192.168.100.50. Similarly, when your logging pod at 10.48.1.6 tries to connect to the same database, its packet also preserves the original source IP. The firewall receives a connection request from 10.48.1.6 to 192.168.100.50. Now the firewall can apply its granular rules correctly. It has a rule that says allow connections from 10.48.1.0/28 to 192.168.100.50, the range containing your billing pods, and another rule that says deny all other connections to 192.168.100.50. The billing connection from 10.48.1.5 matches the allow rule and proceeds. The logging connection from 10.48.1.6 doesn't match the allow rule, so it gets blocked. This achieves exactly the security posture your organization wanted: granular, application-level access control to sensitive resources, while still maintaining the benefits of Kubernetes dynamic pod scheduling and GKS networking features. Meanwhile, if either pod makes a request to the public internet, say, downloading a package from NPM or calling an external API, that traffic still gets masqueraded to the node IP because those destinations aren't in the non-masquerade CIDRs list. You maintain internet connectivity while gaining internal network security. Egress NAT policy. The modern approach. While the config map approach works well and has been battle-tested in production environments for years, Google has introduced a more sophisticated solution called Egress NAT policy. This represents a significant evolution in how we think about network address translation in Kubernetes environments. The fundamental advantage of Egress NAT policy is that it is declarative and application-specific rather than global. Instead of creating one cluster-wide configuration that affects all pods, you can create individual policies that target specific applications using Kubernetes label selectors. This is incredibly powerful in multi-tenant environments where different teams or applications have different networking requirements. Let me walk through this YAML definition in detail. We start with API version networking.gke.io/v1. This is a GKE-specific API that is part of Google's extended Kubernetes APIs. The kind is Egress NAT policy, which makes it clear that this resource is specifically about controlling NAT behavior for outbound traffic. The metadata section works like any other Kubernetes resource. You give it a descriptive name like billing no masquerade on-prem that clearly indicates both the target application and the purpose of the policy. The spec section is where the magic happens. The pod selector uses standard Kubernetes label selectors to identify which pods this policy applies to. In our example, it targets all pods with the label app:"billing. This means you can have billing pods, logging pods, monitoring pods, and web front-end pods all running in the same cluster, but only the billing pods will be affected by this particular NAT policy. The destinations array specifies which destination IP ranges this policy applies to. When a pod matching the pod selector sends traffic to any IP in these CIDR ranges, the policy takes effect. You can specify multiple CIDR ranges if needed. The action field determines what happens to the traffic. Disable means disable source NAT. Preserve the original pod IP. You could also specify enable to force masquerading even for destinations that would normally not be masqueraded. This approach gives you incredible flexibility. You can have different NAT policies for different applications, different environments, or different types of traffic, all managed as standard Kubernetes resources that can be version controlled, reviewed, and deployed through your normal CI/CD pipelines. Comprehensive summary and best practices. Let's consolidate everything we have covered into actionable knowledge that you can apply immediately in your production environments. First, understand that IP masquerading is not just a technical curiosity. It is a fundamental networking requirement that enables pods to communicate with external systems. GKE's default masquerading rules are intelligent and handle most common scenarios correctly, but understanding these rules is essential for troubleshooting connectivity issues and implementing advanced network security policies. When you encounter scenarios where you need granular control over network access, particularly in enterprise environments with existing firewall rules, compliance requirements, or multi-tenant security models, you have two excellent tools at your disposal. The config map approach is perfect for cluster-wide policies. Use this when you want consistent behavior across all applications, when you are implementing organization-wide networking standards, or when you are working with legacy systems that expect specific IP ranges. The configuration is straightforward, the behavior is predictable, and it has been proven in countless production deployments. The egress NAT policy approach is ideal for application-specific requirements. Use this when different applications have different networking needs, when you are implementing zero-trust security models, or when you want to manage NAT policies as part of your application deployment manifests. This approach integrates beautifully with GitOps workflows and gives you fine-grained control without affecting other applications. For implementation best practices, always test network policy changes in development environments first. Use tools like kubectl exec to create test pods and verify connectivity to all required destinations. Monitor your application logs for connection failures after making changes. Document your IP range decisions clearly, because networking configurations can be mysterious to future maintainers. Consider the operational aspects. Who will maintain these configurations? How will you handle IP range changes? How will you monitor and alert on connectivity issues? These considerations are just as important as the technical implementation. Finally, remember that networking in Kubernetes is a complex, multi-layered system. IP masquerading is just one piece of the puzzle, alongside network policies, service meshes, ingress controllers, and load balancers. Understanding how these pieces interact will make you more effective at designing, implementing, and troubleshooting production Kubernetes networking. Please hit the subscribe button if you have not done so already. Thank you for your attendance.